Recall that when we did some of the potential energy to kinetic energy experiments with the ball rolling down an incline, we said that only 5/7 of the potential energy goes into translational kinetic energy. And we said that later on we'd see why. Well, now we can see why. Okay, let's say we have a sphere moving at velocity v without slipping across some surface. Then we're going to be able to conclude that the rotational velocity of a point on the rim of the sphere is equal to the speed with which the sphere is moving in the direction of motion. And that's fairly easy to see. If the sphere starts here and moves a distance delta x to some new position, this is a new position of the center. I didn't complicate the figure by drawing a second sphere with this center. That's kind of hard to do freehand anyhow, and I probably messed it up. But if we move from here to this new position, then a point on the surface has to move an equal distance, okay? And the point of contact again, the point of contact will move an equal distance. The point of contact will move from here to here, so that much of the arc of the sphere has to, or that much of the arc of the circle, it's the great circle through the sphere and the point of contact in the direction of motion. I don't want to go through all that definition, but this point on the surface will move a distance equal to the distance moved by the center of the sphere. And from this you can conclude that the sphere has, a point on the rim of the sphere has a velocity that's equal to the speed of the sphere. From this, and from the moment of inertia of the sphere, we can make some conclusions. So here's a picture of our sphere moving at velocity v along the incline and rotating with the outer rim rotating at velocity v. The moment of inertia of the sphere is 2/5 mr squared. The angular velocity of the sphere, since a point on the rim at radius r is moving with velocity v, the angular velocity is just v over r. And again, that comes just from understanding of what radians mean. And make sure we understand this. Translational kinetic energy is, of course, 1/2 mv squared. There's no argument that since this thing's moving along at velocity v, that it's got a kinetic energy 1/2 mv squared in that direction. But it also has a rotational kinetic energy 1/2 I omega squared. Now what's 1/2 I omega squared? Well, I is 2/5 mr squared, omega is v over r. So our I omega squared is 2/5 mr squared times the square of v over r. So that our kinetic energy is 1/2 of that, which is 1/5 mv squared. So we have a translational kinetic energy of 1/2 mv squared, a rotational kinetic energy of 1/5 mv squared. Means our total kinetic energy is 1/2 mv squared plus 1/5 mv squared, common denominator and so forth, gives us 7/10 mv squared. Since the translational kinetic energy is 1/2 mv squared, which is 5/10 mv squared, then the translational kinetic energy is 5/7 of the 7/10 mv squared total kinetic energy. Okay, we could, of course, put the 5/10 mv squared over the 7/10 mv squared and do this formally, but clearly 5/10 is 5/7 of 7/10. So I'm just going to assert that. Again, it could be done by doing equations. Divide this by this, and you have kinetic energy, translational kinetic energy as a proportion of total kinetic energy. So that's where this comes from. Now again, the change in potential energy, if there's no dissipated force, goes into the total kinetic energy. The total kinetic energy will be the potential energy change in the situation that we studied before, so that the translational kinetic energy, being 5/7 of the total kinetic energy, will be 5/7 of the potential energy change.